Let's do it. All right, today's lecture question, it's more classes, objects, and references. I can't exactly have you draw memory diagrams with the stack and heap for a lecture question, but next week in lab you can count on that. Here's a program, draw the memory and draw the stack and heap, what's going to be in memory, how that's represented, where are the stack frames, where the blocks begin, and things like that. So references, write 3 classes this time. One class named valuable. It's going to represent some valuable item. It has no constructor parameters. It has no state variables. It has no methods. There's pretty much nothing in this class. It just has a name. We can create objects of that type. So working with that will be our question. It's kind of this mysterious thing. How do we work with that thing? Another class named trader. These are going to be people, each who own one single valuable item that they can trade. They're willing to trade with other people. And then a trade agreement. 2 traders can enter into a trade agreement. We're going to do that by creating a new trade agreement with 2 traders as the constructor parameters. And then that has one method named execute trade, where those 2 traders are going to swap their items. And what we want to be careful here is making sure that we swap those items of type valuable, by reference. We want to make sure that we are swapping those actual items. So when I create a new trader with some valuable, and the variable name here, the parameter name, is defined, so you can, in your testing, say .item equals whatever. When they have that valuable, and they're trading that with another trader, we want to make sure that that item that they had when they were constructed, when they came into existence with this one valuable item, that it is actually that item that is being traded. We don't care that the other trader ends up with another item that looks and feels the same and has the same variables. We don't even have variables in this case, so we can't even do that. I'm not even letting that happen. But it has to be that actual item that is traded. And we're going to do that by making sure we're moving those items by reference. They have to refer to the same item. So each trader after the trade is going to have a reference to the new item that they own that used to be owned by the other trader. If the trade agreement is only good for one trade, so if you call execute trade multiple times, it only works the first time. Nothing happens on the subsequent calls. It's just we have a trade agreement to make a trade, then we make the trade. You can't just keep swapping back and forth. It doesn't make sense, so just one trade allowed. And just a note, if you use equal, so write a test suite, test trader. In your testing, you have this situation where you have to check if the references of these variables actually switched between these 2 traders. So we can use the equal operator to do this. If we have 2 objects of type valuable in this case, and we want to know if they are the exact same valuable, we can use equal. We can say valuable 1 equal valuable 2, and that will tell us if those 2 variables of type valuable refer to the same exact object. So equal by default is going to check the references. Do these variables refer to the same exact object? Because every valuable is going to kind of look the same. There's no state variables. There's nothing to really check. But we can check if they refer to the same object. That's the one thing we can check. That's the one thing you should check in your testing. Do they refer to the same object? Any questions on the question itself? This room, damn. Okay, let's see some more stack and heap examples. So we saw a fairly straightforward stack example. We called one method, and we saw when the stack frames were created. We entered a loop and saw when that scope for the loop was created, how that was represented on the stack. We put variables on the stack, we popped variables off the stack, and we saw how all that worked, how a stack frame returns the return value of that method call. And we also saw one object on a heap. We created an object. We called a method that we passed a reference to. And then that method followed the reference to heap space and modified that object, which even though that stack frame ended and everything that had anything to do with that method was destroyed, and that method didn't return anything, we were still able to see some changes that that method made outside of that stack frame, which we call a side effect. That method had a side effect. That side effect was going into heap space and making a change to one of our objects by following the reference. So let's see more examples of this. What we're going to do, just expand things, multiple objects on the heap, multiple frames on the stack. So let's start with this example, which unfortunately is getting a little dated now. Bird Box was a while ago, but we're going to run with it anyway. So let's look at this example, go through this code, step through it line by line, and see how the stack and heap are going to be affected throughout the run of this example. All right, so let's start at our main, and we don't have to understand all the code at once. I'll explain it as we go through. But just top level, we have a class bird with 2 state variables and no constructor inputs. A box that has 2 birds as its constructor variables and no additional state variables, but one method. Each of these have one method that they're going to be able to use. All right, so the first thing in our program, right off the bat, we're going to access heap space. This is, of course, our multiple objects on the heap example. We're going to access heap space. We're going to say operating system, I need enough memory somewhere in RAM to be able to store an object of type bird. A bird has 2 ints. I at least need that much space. Give me that much space so I can store these variables there. It says OK. Gives us some memory in heap space. We don't know where this is on our RAM stick. We don't care where it is. But the operating system gives us a reference to that memory address. It says, wherever this is where you can go to find it. This is how you can find it, and that's what our reference is. So our reference, I just chose some random number, but it's going to give us some reference in heap space and allocate that and then not let any other process touch that spot of the RAM stick. That's ours. That's our memory now for this run of the program. So we create our object of type bird using the class as a template. Create space for the 2 variables, times helpful and times checked. They both initialize to 0. So we have 0 for both of those variables. So we have our bird object. New returns the reference to that memory space. So we can use that reference to find that space in memory. And that's all we store in the variable bird. So we have this variable of type bird, named bird, has a new bird. It only stores that reference so it knows how to find this bird. Doesn't store the bird itself. It doesn't really know anything about the bird, this variable itself. All it knows is how to find that bird in heap space. So how do we go from this variable on the stack to that object in heap space? That's all that reference is telling us how to do, is how to find this thing in heap space. Next, we're going to put another variable on the stack. It's a string. Strings are, I kind of alluded to this last time, strings are tricky, I'll say, in Java on the JVM, so including Scala. We're going to pretend that they just go on the stack. This is technically incorrect. Some of my colleagues will get mad at me for doing this, but we're going to pretend that they go on the stack because that's the way they behave in our programs. They behave as though they're on the stack. So we'll put them on the stack. Yeah.
Where you say that heap stick where in the code, can you explain that heap again?
Explain the heap again? What do you mean by that? That's what this whole example is explaining.
How does this work?
You got to be more specific if you're gonna ask a question like that. If you don't have a more specific question, we can talk in office hours after lecture and things. If you have a specific question, I can answer it right now. Okay. All right. So we're gonna pretend that strings go on the stack. So we'll create this variable named action, put it on the stack. We do technically put the string in heap space and have a reference to it, but since strings are immutable in Scala, they behave as though they were on the stack. So we can pretend they're on the stack. If you do put them on the heap, I'm not gonna ever fault you for that. But since the values can't change, we don't really have this reference, this whole idea of a reference. It doesn't behave that way. So we'll just pretend, that they're on the stack. So to get technical into it, if you are reading documentation, it says strings are going on the heap. Yes, but we can pretend they're on the stack just for simplicity's sake. With that said, okay, we get to our if statement. We're going to start a new stack frame. We hit a new block of code, which is whenever we hit an open brace. But we hit a new block of code, and we're going to execute this Boolean expression. We're going to resolve this expression, bird.endanger. So we have our variable bird. We're going to access its value, which is a reference to an object of type bird. That tells us where to go in heap space. And then we're going to call its endanger method, which is going to take times checked. I should, for clarity, put this dot times checked because we're accessing a state variable. This dot times checked, increment that by 1. This object's, that reference we found, this object's times checked variable is going to increment by 1. And then we're always going to return true. So we went to heap space, incremented times checked for that particular object, and then return true. So we are going to execute our conditional, our if statement is true, so we're going to run this block of code. We create a variable named action, set it to the value panic. We reach the end of that block of code. So we destroy that variable that we just created. We create a new value named action with the value panic. Hit the end of that block. Since that value was created within that block, we destroy it. And then when we print action, we're actually still printing nothing. So this line of code didn't actually have any effect on our program. We created a value, set it to a value, a string literal, and then destroyed it right away. And then when we checked the variable action, since we're outside of that code block, that value action was already destroyed. And we reverted back to this action. So this is the action that's currently in scope. It's the only action on our stack. It's the only one that exists on the stack. So that's the value we get. We print nothing here. So with this val, if we just did action equals panic, then the program looks in this block for a variable named action, doesn't find it, expands the scope of its search, finds this variable, then changes it. That's not what happened. We declared a brand new variable named action, so that gets destroyed at the end of the block, print nothing. So we have to be careful with our scoping when we're working with blocks. And of course, you were affected by this in 1.15, but now we want to explain what was going on, how was that happening. It's because that stack, that block, the end of that block was reached, so everything contained in that block on the stack was popped off of the stack, and it was all deleted, all destroyed. Now we get to quite a mouthful for a line. We're creating a new value named box. Actually, that's not going to happen until after new resolves, but we're calling new, creating a new box, and giving it 2 parameters. It takes 2 birds. We're giving it as the first argument, giving the bird that we already created, which has this value. So we're giving the value 42976 as the first argument, that reference to a memory address, and then also creating a new bird. So new bird is going to allocate memory for a new bird. We're going to ask our operating system, every time we see the keyword new, operating system, give us some space somewhere on our RAM stick to store a new object of this type. We get that. I picked a random number because we don't know, we don't care, but the operating system is going to give us some reference to some memory to be able to store that object. We get 2 new variables, times helpful and times checked, completely different from the variables associated with this object. They behave independently, they're initialized independently, completely different variables attached to different objects. They just happen to have the same names, but they're in different scopes, so that's allowed. So we created that new bird. got the reference, but we never stored that reference anywhere in our main method. We just, whatever reference this resolved to, we put it right in our box immediately. So when we call the box, we have this reference and this reference as our two arguments. Create the box, say operating system, I need enough memory space to store a box. It gives us some reference. And then we assign those two values from the constructor in that box. And again, these values are objects, so they're just the references to those objects since we're passing in a class type. We only get the references. So this box has references to two birds. Doesn't really know anything about those birds directly. It just knows where to find them in heap space. That's all the box knows. So when we call, then we create our box value, put that on the stack, and give it this reference. And notice these, for example, this value changed on this bird earlier, but this bird variable we have as a value. The value that's stored in this bird variable is not changing. That won't change throughout this whole program. So we can use val there, even though the bird itself, its state variables are changing throughout the run of the program. The value stored in the variable bird is always just that reference to that memory address. So val there, perfectly valid. Val here, perfectly valid. And then we don't really use, val here and here, all perfectly valid because those references were not changing. Sometimes we do want to change references. For example, updating a list, creating a new list, and reassigning it a new reference, but not in this case. All right, so we put box on the stack with that reference to the box somewhere in heap space, and then we move on. Here we have a call. Technically, we have multiple frames on the stack, but we're not going to worry about it too much for this example. Next example, we'll hit a bunch of frames on the stack. But here, we're calling box in danger. So box, go to this value. And for this box, this is the calling reference. Go over to box, the in danger method, and call this on this object. So bird 1, bird 2, that's going to refer to this bird 1 reference, bird 2 reference. So bird 1 in danger. We're going to go to this method. Oh, I meant to update this one. But it's going to go to this method of bird 1. So we're following this reference. We're going to this bird and calling this bird's in danger method. So when I access times checked, I have this variable right here. This is the variable that we're going to look at to be able to determine what happens in this method. This method is going to increment that by 1. And then return true. Yeah, it pains me. I gotta give one of these side notes again. Technically, if you run this if you run this code, this value would not increment by 1. I gotta avoid these technicalities. We get sidetracked, but this value wouldn't increment by 1. Since this is an OR condition, once this is true, we'll actually shortcut the OR. Once we have true or anything, it's always going to resolve to true. So the Scala actually won't evaluate this next method. This will actually never be called. Since this is true, it doesn't matter what that is. True or anything is going to be true, so it just returns true without finishing the expression. So technically, this would still be 0. I accidentally had that side effect in this example. I meant to update it, but I don't always do that. Don't always find time. All right, so action. Since this was true, we're going to hit this line, action. Since we're not declaring action again, we're not saying val action of type string equals this, var action of type string, whatever equals this. We're just saying action. Now our program is going to look in the current scope for this, for a variable named action. Not going to find it in this if block. There's nothing in this. Nothing was declared within this block. Then it's going to expand it, search, look outside of that, outside of the block for a variable named action, finds it, and then assigns its value to stay in boat. Hit the end of the block, get rid of that block, then we print action. There's only one variable named action on the stack, so it's easy to find the right one. It has the value stay in boat, so we're going to print stay in boat. So the big takeaway here is how we're creating references, creating objects on the heap, and how we're following references. Every time we have a reference and we use the dot operator, we're saying go to the memory address of this reference, find that object, and then whatever variables, whatever state variables that object has, call its method, access those variables, do whatever, but do it with that object in heap space. And we free all the memory, all the stack and heap, all that's freed up at the end of our program. Any questions on this example? There's a good number of moving pieces here. Let's take a little bit to digest this. Any questions on this one? Yes?
In the second if statement, if you were to write val action equals stay in the boat, would you not be able to print stay in the boat? It would just print nothing?
In the second one, if I did if val action, oh, right here, if I did val action equals stay in the boat, then it would print nothing right here, yes. Yeah, because that would create a new variable named action in this scope, which is allowed because it's different scopes, so we can have the same variable names that are already on the stack. But then when we hit the end of that scope, that new variable we just created would be destroyed, and this variable was never touched in that case. So we'd still just print nothing. What language? This is Scala. Oh, it was already answered in chat. What's the point of bird 2? Why didn't the value ever change in panic? Which one was panic? Oh, why this one didn't change? Because we created a new value. So it did change, but it created a new variable named action in this scope, in this block for this if statement. Create a new variable named action, or value in this case, set it to the value panic, but as soon as we hit the end of that block, everything declared in that block was destroyed. And yeah, what's the point of bird 2? If you've seen the movie, what's the point of any of these birds? They're kind of useless in the entire movie. What's the point of bird 1 even? Any other questions on this? All right, moving on. Multiple frames on the stack. We technically had multiple frames on the stack for a brief time in that previous example, but it really wasn't the focus. I really wanted to see multiple objects on the heap and how we follow references to visit each one of those objects and how we're storing those references in variables. Now let's talk about multiple frames on the stack. And for this one, we won't even have anything in heap space. We're just going to focus on the stack for this example. So for this, we have a recursive method again. I said this last time, I believe I did, I at least meant to, but you're not expected to fully grasp recursion yet. It is a topic for later in the course, but I do want to tease it a bit. I want to show you some recursive methods in some of my examples, just to get you used to the idea that recursion is a thing that exists. And you should be able to at least follow the example as I go through it. What I don't have the expectation that you understand at this point is being able to write a recursive method. Writing recursive methods takes some practice. It takes some kind of different way of thinking. So I don't expect you to be able to write them now, but we should be able to follow the execution of a recursive method. So with this one, we want to compute the geometric sum of 3 So we want to have 3 plus 2 plus 1. We expect this to return 6. So let's trace through and figure out exactly how it determines what it's going to return and just how we get there. So first, main method. We've seen this before. We're going to have a method call. We're eventually going to assign that to the variable result. But when we call geometry, we're going to create that parameter as a variable in the new stack frame that we create for this method call and assign it the value from the argument. So our argument is just the literal value 3 as a magic number. We're going to assign that argument to the parameter n when we start in this new stack frame. Our entire method is a conditional that's going to determine what we're going to return here. If the input is greater than n, that's true in this case, we're going to start this new block, this new if block, and this if block is going to call geometric sum of n minus 1. So we're calling this method from inside the method itself, which is where we get the definition of recursion. A method that calls itself is a recursive method. So compute geometric sum just created a new stack frame with an expression that evaluates to 2. So we're going to create a brand new stack frame. The parameter n is created with the value equal to the argument. So we have an n equals 2. So right away we notice that we have two values of n on the stack with our two variables of type n, I guess they're values of type n on the stack with two different values that they're storing. Yet we can still run this program and have the program know which value of n to look at. In this case, it's simple. They're in different stack frames. They're in completely different areas of execution. They cannot see each other. From within this method call in this stack frame, we can't even access this value of n. So we know that this value of n is going to be the one that's used. When we call this method, the first thing we do is call it again with the value 1. New stack frame, new if block, new stack frame, new n, new value of n. So now we have 3 n's on the stack. But that's okay because they're all in different stack frames. They're not affecting each other. They can't be seen from each other. We just have 3 values of n in 3 different stack frames. No big deal. Now we have n equals 1. It's still greater than 0. New if block, new stack frame, new n, new value for n. And we just keep running this. We keep adding new stack frames. And it's just not a big deal for us. Now our condition is false. 0 is not greater than 0. We're going to hit the else. And now this stack frame finally starts returning. So this stack frame hits a return. It's going to return 0. That whole stack frame is destroyed. That value of n is destroyed. And we're going to return just 0 from that stack frame. Now we can resume execution from the previous stack frame. The stack frame that called that method is going to get the return value and pick up right where it left off. So what we were waiting for was this expression to resolve, this method call to resolve. Now that that's finally resolved, when we go back to this stack frame, we can pick up execution there, get our value of 0, create the variable result of type int, and assign it that value of 0. So now we have that value 0 in result, and we can continue execution on this stack frame. We get to the next line, we're going to add n to result, which was 1. So n, we're going to look within this stack frame. Within the if block, we don't find an n. Expand our search to the stack frame, find the n, value 1, 1 plus 0, return 1. This whole stack frame resolves to 1. That's what this returns. Now in this if block, in this stack frame, we can continue execution, which was waiting right here, and do the same thing. Okay, we create result. It got the value 1 from this call. Add 2 to that. That's our value of n here. We got 3 in result. Return 3. This whole stack frame returns 3. Now this stack frame was waiting right here for the return. It gets 3. Result is 3. n is 3, so we add 3 and 3. We find this value of n, return 6, and that's what's finally returned over here. The main stack frame was waiting that whole time for that top level recursive call. That call finally returned 6. We create a value named result, assign it that value 6, and finally print 6 to the screen. Any questions on that one? I went fairly quick through that, so I hope there are some questions. Yeah.
Wouldn't it be easier to just use a while loop?
Yes. So the question, wouldn't it be easier to just use a while loop in this case? Yeah. A while or for any kind of loop. When we do talk about recursion proper, we're going to see specific applications where recursion is called for and where it helps us out. In this case, yeah, just use a loop. This is actually more wasteful. It puts all those frames on the stack. It takes up a bit of memory. It's a bit more inefficient than just using a loop for computing geometric sum. I just wanted to show a recursive example. The loop doesn't put all those frames on the stack. You have a question?
Yeah, what can you add put this on the camera for the statement?
What was it?
Can you just add like 1, 2, 3 and this, then we can resolve.
Yeah, so why do we do all this? That was the last question. Why are we doing all this recursion and everything? Just because I want to show off stack frames. And if I don't write here, I'll tell you why. If I didn't do a recursive method and I want to show off stack frames, I had to find like 3 or 4 different methods and have them all call each other and have this big convoluted mess of code. The recursive method gets me, I got 3 or 4 frames on the stack with not a lot of code. You can see the code, you can understand it quick, and then I can focus the conversation on the stack frames, is why I did that. I just wanted an example that gives me stack frames without a lot of overhead. Yes? Yes. So if I have like the previous example where I had 3 things on the heap, each time I run that program, I can get 3 different spots on the heap. It's not necessarily the same every time. Was that your question? Yeah. Yeah, so every time I run my program, that program, each time it hits the keyword new, it's going to the operating system for a new space. We might just happen to get the same spaces each time. If that's the only process running on our machine, the OS might just go through the same logic and just happen to give us the same spots of memory, but there's no guarantee that that's going to happen. The operating system's just going to do whatever is most convenient according to its algorithms and everything and find whatever memory it decides to give us. And it'll just give us a reference to that. Every time we run the program, we might get different memory.
So what if like you're doing a lot of other stuff in the background,
So if you have a lot of other processes using up a lot of RAM, so you eventually can just run out of RAM. And that's when your machine really slows down. So what happens when you run out of RAM is your operating system will start what's called paging. It'll start using your hard drive as RAM, which is significantly slower, reading and writing to disk every time, way, way slower than RAM. So once you run out of RAM, your programs can still run because the operating system will pretend the hard drive is an extension of your RAM, but it's a massive slowdown. If you've ever been running a lot of stuff on your machine and everything just slows to an absolute crawl, it's probably because you've used up all your RAM and you're using your hard drive at that point. So if you have a lot of other programs running it, but when we get heap space allocated to us, the operating system will prevent any other process from using that space. So once we get the space allocated to us, that's ours. Like we get to use that. At least we get to use that reference. It might internally move that around in RAM, but we get that reference and we're guaranteed to have some space available to us. Right. What's that? Like once the operating system says, yeah, here's enough memory to store your object, we're guaranteed to always have a reference that's going to have our object. It's never going to go back to us and say, hey, you know what, I'm taking away that memory. You can't store that object and you can't access that object anymore. It won't do that because then our programs start crashing. Any other questions on this one? Ooh, good question. So our program in the previous example worked pretty good because once our condition was false, we returned 0 and we stopped creating new stack frames. We stopped allocating more stack space and we started returning those stack frames. We returned 0, then the next one was able to return, the next one was able to return, and we started deleting frames off of the stack. What if we didn't? What if we didn't have that conditional and we just kept putting more and more frames on the stack with no what we call a base case to our recursion? What if we didn't have that base case and we just kept recursing over and over and over? So when we got to this point, this is where we started returning. N was 0. We checked our conditional. 0 greater than 0 was false. We returned 0 and started destroying frames and start returning up the recursion. Without that conditional, when n was 0, we're going to make another call in the stack. We're going to create a new stack frame of with n equals -1. That's going to create a new stack frame with n equals -2. That's going to create a new stack frame with n equals -3. That's going to create a new stack frame with n equals -4, so on, so on, so on. At some point, something's got to break this cycle, and it's going to be when we hit the space used by another program or any space that the operating system did not allocate to us. When our program starts, the operating system says, here's your stack space, this is what you can use. Once we get to the end of that stack space and we try to use the next byte of memory, that's when we get the stack overflow. So this is what the namesake of our favorite site, Stack Overflow, is when we use up all of stack space and try to use just 1 byte more. We overflowed the stack, program crashes, can't run anymore, nothing happens. So we had an infinite recursion, Stack Overflow, crashed our program. So if we don't have a base case to our recursion, if you're writing recursive methods and you see these stack overflows, it's almost certainly you didn't have a base case and you filled up all of stack space and we're not able to run that program. Brings us back to any other questions on the lecture question? Let's run a little code here. Not OBS. Give me my mouse. Examples. So here's our method. If we run this, with our base case, everything's fine. It's the example we saw where we returned 6. And just to verify, yes, we do return 6. I'm going to do this on Friday. I want to give a lot of examples of this. I want to give you a taste of it today. If I set what's called a breakpoint, I can use what's called the debugger. I highly, highly, strongly recommend this. All the TAs will recommend this. This is something that can save you hours and hours and hours of programming. If I set a breakpoint where I just click in the sidebar here, and then instead of clicking the run button, I'm going to go to debug right next to it, this little bug icon. What this is going to do is run my program, but it's going to stop at my breakpoint, show me everything that's going on in my program, and allow me to step through this line by line as though it were an interpreted program. So if I do this, and that's right, I get all of the frames on the stack, and I can see, and I can see each frame, what's happening inside that frame. So if I go in my main frame, I have my command line arguments, which we're not using, and I have a reference to this, which just gives me some stuff, some information we're not concerned about right now. But if I click this button here, I'm going to start stepping through my program and see what's happening line by line. And I can see all the values of these variables line by line. So here, I put a new frame on the stack. In this frame, I have a variable named n of value 3. I'm going to check that conditional. It's going to be true. I'm going to run this line. That's going to put another frame on the stack and another frame on the stack. And I can see all my stack frames here through the debugger. So IntelliJ is going to show me all those values, everything we just stepped through in those examples. If you want to run your own examples, write your code, run the debugger. You can see all the stack frames. You can see the heap space. If I look at these, okay, n, it's 2 there. In this frame, 3, 1. I'll highlight the line that I'm running on. If I keep stepping through this, I get to the return of 0. Start returning stack frames. We'll see these stack frames start disappearing. And we start returning those values back up that recursion until we finish this execution of this program. So we can see all of that stuff we saw, all the heap and stack. This example is only stack. But I'll go to the heap one in a minute. But let me rerun this with our infinite recursion, with our stack overflow. Just I want to show what that error looks like in case you ever see it. So here we're going to do the same thing, but we just keep putting frames on the stack. Frames on the stack, frames on the stack. We can see at this point we have all these frames on the stack, and our n is -9. We can keep running. I'm not going to click this until the stack overflows. What we can do in the debugger is hit this resume button, and that's going to run our program again until it hits another breakpoint, which my breakpoint is in main, so it won't stop again. I hit this, we're going to get our stack overflow. So now my stack is just filling up with stack frame after stack frame after stack frame. If I go to my console, stack overflow. So I got the stack overflow error on this line. That was called from a stack frame, calling that line over and over again. You can see that's how many calls ended up going on the stack. Quite a few, I'm not going to count them, but quite a few calls on the stack, quite a few frames on the stack before that overflowed. So we have quite a bit of memory to work with here. But if we're going infinite, we're obviously going to use up whatever it gives us. Bird box main. So let's do the same thing with bird box. Run this in the debugger. Compiling. And when we have a variable called the constructor, run all the code outside of the methods. When we have a variable that stores an object, we can see the variables for that object, but we can also see right here, we're going to get that at some number, at 587. That's going to represent the reference for this object. So I'm not actually storing this object, I'm just storing this reference at 587. That's the value I'm concerned with. And that value, my debugger is going to show me, okay, at that memory address, we have these two variables with these two values. So the debugger is going to show me what's on the heap space, but whenever we see this at, we have something of type week3.memory.bird at this reference. Now when we step through this a little more, here we have action. Oop, I need one more line. How did I not get that other action? Might have already destroyed it. Well, we should have had two actions on there on the stack. I think I clicked through it, maybe. But when we get to When we get there, when we create this box, we can see we have two birds in this box. The first one has that same reference. First one has that same reference, 587, as the bird in that bird variable, because those refer to the same exact bird. This is the same bird in heap space. And when I expand this, times helpful, times checked, we're going to see those same variables. We're going to see 0 and 1, 0 and 1. That those could just coincidentally end up being the same. But when we look at this reference, we see that this is the same bird in heap space. That's the same exact bird. The other bird is going to be at 962. This bird we don't have, the box is at 962. The other bird is at 961. And this is going to have different variables. It's not the same bird, but it's also a bird we don't have a reference to otherwise. The only way we can access this bird is through that box. We have to go through the box to get that bird. We don't have it in a variable anywhere else. If we... And we can verify what I said earlier, that bird2.inDanger is actually never called. We shortcut that, return. Bird2 times checked is still 0. Well, times checked up here is 2. Technically, that one didn't happen. I'll have to update that slide. I won't forget this time. And then print nothing and stay in boat to the screen. I highly recommend when you're debugging, when you're trying to figure out what your program's doing, you got something that you just don't know why it's happening, set a breakpoint, run the debugger, step through your code, and look at all of the values for all of your variables. The debugger will show you all those values. Look through that information. It'll really help you see what's going on with your programs. Yeah. Yeah. So the breakpoints where things are going to stop. So I said it at the beginning of my main on both of these, but if I'm interested in this line, if I know I have a bug that's somewhere in this area, I can set my breakpoint there, run the debugger, and it's going to run my whole program up until that breakpoint. That's where it's going to stop, and that's where it's going to start showing me all kinds of information. And debuggers are very powerful. They can do a lot more than just show you the variables, but this is, I don't know.
You can also show what kind of bug you have.
Yeah, it'll show you all kinds of information. And you can set conditional breakpoints. They're very, very powerful tools, but setting a breakpoint and stepping through your program, that alone is so valuable, so helpful, can save you so much time. Anyone have questions? Anything else? Reached the end of my slides and the end of my examples, so let's get out of here. See everybody Friday.